Hello everyone, welcome to the Science Club podcast. I'm your host, Jocelyne Sofia. Hello to you, Sofia and Filip. Welcome to my podcast. Sofia is an astrophysicist. Filip is a nuclear physicist.
Yeah, hi. Thanks for having me.
Thank you.
Sofia, tell us a little bit more about yourself.
Sure, yeah, I can introduce myself a little bit more. As you mentioned, I'm an astrophysicist. I'm actually originally from Chile, when we have one of the most beautiful and clean skies in the world. And yes, and so I did my bachelor and my master's in Chile, and then I went to Switzerland to do my PhD to focus in extragalactic astrophysics, so like the large-scale structure of the universe and its connection with the galaxy formation and evolution. And I'm currently in California, in Pasadena, in Caltech, doing a postdoc with a very nice professor called Chuck Steidel, studying in particular a very nice time in the universe and galaxies and how they interact with the gas around them.
So I'm originally from Poland. I started as a mechanical engineer. I've done my master's there. Then I moved to Zurich, Switzerland, as Sofia, but not to study astrophysics. I actually changed fields a little bit. I was working in thermodynamics, in nuclear safety research. So I was looking into how to prevent and how to estimate the potential disasters in nuclear power plants that are, I want to make the point here that they are very unlikely, but we were still researching how to make them even less likely, and in a very unlikely case that they happen, what could be done to minimize the fallout, right? And afterwards, I finished my PhD here. I moved to Luxembourg. Now I work in the team of Professor Stefan Leyer. So, it's now my research is not focused so much on nuclear installations, but in general thermodynamics. So, heat and mass flows for different industrial practical applications, stuff like desalination or fuel flow in rockets, rocket engines. These are it's a wide area because, matter and energy is flowing all around us in many very different applications. So, yeah, we're trying to research many of them. So, yeah.
There are some interesting aspects to your profile and what you've just said, because there is a switching of fields and important applications about what your work as well, and the impact that has, which is very important in science, because much of what's going on in research, it's not necessarily applicable to everyday issues of everyday life. It is nevertheless important. Research which is more theoretical, it's basically like a small gear rotating very fast, and rotating the big gear, which is rotating slower, but the torque of the big gear is going to be much bigger. So they're not that fast here, but fast enough to at least lay the basis to have a bigger impact on the bigger scale. So the bigger scale is actually this torque, this bigger gear, and bigger gear is actually all the application of theoretical research. I'm not trying to say that theoretical research is always useful. And there is actually a paper called the usefulness of useless research. So you've got like something which is like a part of the theoretical research, which is apparently useless, but it's never useless actually, because if we did physics just for a practical purpose, we would stagnate. So that's the problem.
Well, actually, I believe if it's used as a base to create some technological marvels, then I believe our lives can change quite a bit. But just from understanding directly, probably not. But it's still worth doing. So yeah, let's keep on doing.
It is important and fundamental, in my opinion. It's extremely of extreme importance to do theoretical research. It's needed. You just can't make changes. You can't advance science without theoretical understanding, theoretical research. So you need to come up with. There need to be absurd topics and absurd research, if you want to define it like that, which is completely useless to most people who look for applications. However, that's what leads to revolutionary understanding, and that's necessary. And some people do not believe, basically, that if we keep digging, we can add to what we know. And that what we know, thanks to the facts that we've been doing it so far, that we've been continuously, we kept digging and deeper, we managed to gather this knowledge. We need research is of fundamental importance. I mean, you can't advance anything in the world if you don't invest on research, and especially on theoretical research. There's a lot of open questions, different fields, like you both. And my background is basically a mixture of high energy physics and astrophysics, but in mathematical physics, but I'm more into the theoretical direction, a little bit less of astrophysics than Sofia, but more towards particle physics, quantum field theory, and from mathematical perspective. Sofia, you said that you're an extragalactical astrophysicist. First of all, you said that you're based at Caltech, so Pasadena, one of the top rated universities, just like to mention.
Yeah, it's amazing.
Which is also important to have a stimulating environment. And I'm not saying that universities which are not ranked very high are not necessarily not good, not stimulating, but there is competitiveness, and which is pretty constructive, that contributes to developing an excellent research. So you said that you're based at Pasadena, and you're a scientist, and you're a researcher, so that's important. So it means that you're already graduated and that you're working. Technically speaking, you're both postdocs, so that means post-graduation, right?
Yeah, but I feel like I'm an eternal student because I'm always learning.
Exactly. So that's a little bit of the point of being a researcher. So you keep researching and you keep learning. And that's beautiful, of course. However, it's so it can be very challenging, because academia is a challenging environment, and we're going to talk about the challenges that are within academia. But how do you combine your private life, or can you tell us a little bit more about your current situation and how you live? I mean, not too personal details, but I would be interested, knowing how you focus on your field and what you do in your outside your work.
I think it's always the search for equilibrium, for balance. As you mentioned, I'm working in a very, very exciting and very challenging environment because it's focused on the excellence. So it's very important to try to find this excellence in a healthy way for yourself. And a lot of struggles that especially women face, and I think many people, it's like a common symptom in academia, is to feel that you're an imposter, that you don't belong here, that everybody is will realize that you're a failure, or I don't know, you did something lucky to get where you are. So in order to have a balance, to feel yourself that you're worth it, and you can have a very healthy relationship with your science, is to actually find spaces to liberate yourself, to not be focused when it's supposed to be focused, and to let your mind rest when it needs to rest. Actually, subconsciously, you're always like thinking of science, and sometimes you came out with answers when you are in your free time. So I value myself a lot, what I do outside of academia too. Besides a scientist, I'm a musician. I play the violin, I sing. I started painting very recently. I really like doing a lot of hobbies, and spending time with very diverse people. I like interacting with people from many backgrounds, especially here in California, where there's so many people from so many backgrounds, and in university environments are always very diverse. And I really like that. So I think actually it makes me a better scientist when I have myself this space to interact and to discover and to feel like I'm a diverse person, because I drive this diversity to the questions that I ask myself on how to solve the problems that I have to solve.
So I've got actually quite a few remarks about what you just said. So you told us quite a few interesting aspects of being a scientist and being a researcher, and especially interested in science, such as the fact that you keep thinking about science, and that can be actually draining, because especially when you're a student, there is like this vicious cycle that you fall into. So you're never free, because you keep thinking about, like, not even work, because you're just studying, and you want to prepare for your lectures, you want to understand, but at the same time you need to rest. And whenever you're trying to rest, you think about, no, I have to get some work done, I have to do, like, prepare for exams, I have to do some exercises, I need to keep going. But the minute you sit down and you try to focus on your work, then you sometimes it's very hard to do it. And the only solution to that is just rest. Take a day off, take whatever, do whatever. Don't focus, don't study, you need to rest, you need to reset your mind. And that's very difficult, a very difficult thing to do. And especially when you're a researcher, you keep thinking, I mean, it's unavoidable. You can't just, if you like what you're doing, and usually when you're a researcher, you usually like what you're doing, because that's the reason why you chose your field. It's very problematic, because your mind keeps working, and you keep thinking and connecting the dots, and you keep coming up with ideas. And especially if you're creative, which is like very often is quite consistent with being a scientist, it motivates you to in your daily life, actually, because you get out, you observe things, you search for patterns, you look for hints and ideas, but that drains you as well. So you need, like, at some point you need some space in your mind. You need to empty it, so that you can just, like a RAM, you've got like this short-term memory and RAM. But as you said, that relates to the imposter syndrome, which if you're quite ambitious, tendentially you end up having it. It's very common, but it's very common among people who want to get things done properly. And the main issue is that you don't want to disappoint people, but above all, you don't want to disappoint yourself. And you feel like if you're taking a day off, if you're resting, you're not doing the right thing, because you're just missing out on what you should do.
I'm lucky that I don't have a family.
I wouldn't say that, because
no, I mean, yeah, you know what I mean.
Just 3 points.
I would say it's much easier to relocate
from ETH, from Zurich, because you graduated, you did your PhD actually in Zurich.
Yeah, I graduated in 2020.
Exactly. So now it's 2022. Mm-hmm. So I suppose you moved. Did you move on your own? Yes,
I moved on my own, and yeah, I just have to say that it's quite easier to relocate when you don't have a family. I know that's struggle for many other people, and yeah, it's a thing of academia that it's very nomadic, and you have to constantly move around the world. And for some people, it's a struggle when you have a family.
And so you can also find the time to focus on your research and do some free time activities which do not necessarily consume you, like some who've got families who enjoy them, but it's still kind of time consuming because you have to really stick to schedules which are very strict.
Yeah, I mean,
more
when you have a family, you're much more constrained on the things that you can do, but at the same time, it's a different, how can you say? It's like, it's a limitation in a certain way, but there's a lot of diversity within that limitation. It's not like it's a bad thing, So they're like maybe more restrictive, and there are many more things that you cannot do, but the things that you can do are very worthwhile if you enjoy your family.
I would define that personally because I've got myself family and I've got a daughter. So she's 6 now. And by the way, I graduated with my daughter at ETH from, I graduated in 2019, the master's degree, by the way, so in theoretical physics. And it can be having a family, especially if you've got children, it can be a big motivator to achieve more. You've got like a reason, to invest your energy on. And you, Philip, are in Luxembourg.
Yes, I'm actually splitting my time a little bit between Luxembourg and Switzerland. Because I got married in 2020 just as pandemic started.
Congratulations.
And, thank you very much. I mean, my wife, Sagata, she's still in Zurich in Switzerland. So, it's only 400 kilometers distance, but it's still large enough that it forces us to make some compromises. So, yeah, I agree. In a way, family is a constraint, but at least in my situation, it's not that bad because it's maybe not a nice thing to say, but in a way, the COVID pandemic was a welcome change of modes of working, right? Home working became much more available, and this helped us a little bit to keep the relationship going, and the whole long distance thing. Sorry, keep it a little bit more limited. So, yeah, it's about finding a right balance, and I'm at the stage of my career that nothing is fixed. I don't know if I will make it in science yet. Academia is very competitive, and the open positions, permanent positions, are just very scarce. So it might be that I'll have to switch probably into industry. But in any case, the situation is temporary. So at least knowing that only for 2, maybe 3 more years, we have to keep it separated a little bit. It's helping, And in any case, whatever the outcome is, if I become a professor, if I move to industry, at least the long distance thing will be finished. So it's okay.
That's one of the main concerns about scientists who graduate and they have to make a choice. Either the country where I currently live at the moment, or academia. And that's a hard choice, by the way. So it's a very tough choice for some people.
To this, I guess this really depends a little bit on the field.
You mentioned that you switched fields, you changed at some point, and you're doing you're more of an experimentalist at the moment. So you.
Oh yeah, it's not like I didn't completely change fields, I could say, because what I was doing before during my PhD, it was still fluid mechanics and thermodynamics, just the application was particularly focused on nuclear power plants and in particular pressurized water reactors. And now I'm applying more or less the same tools, just to different problems. So, as you know, nuclear energy is not extremely popular in Europe right now. Maybe it's making a comeback. In recent days, the European Union designated nuclear energy as a green energy source. So that's a win for us. Again, Sorry?
There was a bias against it. So there's still.
I mean, there is a huge bias, and it's first off, it's in people. They're afraid of stuff they don't understand. Everybody remembers Chernobyl. Everybody remembers Fukushima that happened not that long ago. And this public pressure is influencing political decisions. And as a result, they're not made based on facts, but more on political capital, right? Unfortunately, this reflects on science and which projects are funded, which projects are not funded. So even at this stage, even if your work project or your research project would be somehow applicable to nuclear energy or nuclear power plants, maybe it's best you don't mention it, or at least it was like this in the last years. Maybe right now it's changing, and I hope it is, because honestly, at this point in time, we don't have an alternative. So, yeah, but going back to changing fields, I'm still doing fluid mechanics, thermodynamics. It's just not so much about nuclear power plants anymore.
But I think that there's this bias is it to some extent may be justified, because the impact of an accident is way bigger, because the impact of a potential accident is way bigger than it's huge.
Well, but not at all, actually. If you look into the details, what were the results of the two biggest catastrophes, and then compare it to how many people are killed every year by pollution that's caused by fossil fuels, it's just not comparable, really. And to add to this, the nuclear power plants that are produced today are insanely safe. This is the same thing that happened with aviation industry, right? At the beginning, there were catastrophes, people dying, but everybody was learning from it and improving. So right now, the modern reactor, in the worst case, what can happen is that it will shut down. It's just,
But so there's measures which have been developed. Yeah, sorry.
No. I mean, I'm just wondering if it's a fair comparison between nuclear power plants and carbon energy. I mean, are there any other alternatives which can be better than nuclear, or is carbon
not really
alternative?
I mean, yes and no, right? Because we have renewables, which are great, and they have to be developed in tandem. But what renewable energy cannot do is to provide a constant baseload, right? What happens is that wind, solar, those sources, they are extremely variable in time. And we don't have capacities to store this energy. So you need something more reliable that provides this constant supply through the night or through the times when there's no wind. And, nuclear fusion is the dream. Everybody would like to have this, but it's not there yet. And we don't really know if it's going to ever get there. So either we develop extreme.
You work on that.
I really hope it's going to be completed maybe in the next decade, but we cannot count on this, right? It's research. You never can count on anything. So either
the comparison that you make, it's pretty accurate. It's like exactly like with planes. People, well, I'm afraid of flights anyway, so I don't like flying. I mean, I do fly, but I don't like it. So I get anxious every time I have to, fly somewhere. But it's the same. I mean, people, because they assume the worst case scenario and tend not to pay attention to statistics, but the impact that a single catastrophic event may have. And in the case of nuclear power plants, it may be, or at least it has been bigger. And
if you're talking about the single particular event, then yes, that's true. Yeah, but what you have to do really is to consider the total amount, right? Like people are very worried about nuclear waste that's produced by the power plants. But what nobody is thinking about that when we are burning coal, you are also producing nuclear ashes so radioactive ashes. And by quantity, this is way more than all the nuclear power plants are contributing to. So you really need to look at the whole life cycle. And,
yeah, of course. I mean, that's all parameters. I mean, it is, but that's the problem, that generally speaking, people take things out of context and they don't look at the entire, all the parameters. They just take the one that may have, maybe the biggest weight, but maybe it's not necessarily the one happening the most often. So it's the least frequent, although it may have a bigger weight. But as you said, you have to find solutions which take into account all these parameters, and there is an amount of CO2 and greenhouse gases which the damage is already there, so it's going to be difficult to avoid climate change, and that's a big issue, a very hot topic I like talking about. It's very hard to find a solution to that. So maybe I can ask you, so how do you see if we replaced the fossil fuel we're using mostly at the moment with nuclear power plants? So how would that help us to reduce? Do you know what's the impacts that may have in terms of reducing the amount of CO2 produced?
I mean, I don't have any hard numbers. I'm sure we could look it up, but basically nuclear power plants are not emitting CO2 besides the construction phase, right? When you're using concrete, transporting materials. So this is not producing CO2 during its operation, right? But this is only part of the equation, right? Because this is the energy that we're using in our homes in the form of electricity, but we are using a lot of fuel for transportation, right? Planes,
exactly.
cars, ships. So I mean, the nuclear power plants are not gonna replace your car engine, or maybe, I mean, some ships are nuclear powered, that's doable, but these are moving vessels, so probability of any sort of accidents is much higher, so maybe not the best application still. So we would have to consider a way of transforming the heat that you essentially get from a nuclear reactor into fuel that could be later utilized in conventional transport. So either some sort of hydrogen-based transportation. I mean, it's an extremely large task in front of us, but if we want to avoid really destroying the planet, I don't think there's an alternative. Even maybe a step further, what we will have to do is to run some sort of carbon capture technology to suck out the carbon that's already out there.
There are some people working on that here in Caltech. Yeah,
many people.
I mean, here in Zurich as well, but it's extremely energy. It's consuming a lot of energy, those processes. So you really need to step up the energy production.
Yeah, and I think Elon Musk has actually proposed a $1 million prize for someone, if there's someone who can come up with a plan, of course, with an efficient plan to carbon capture, actually. So capture from the atmosphere as much as possible, actually. But according to the Paris target, we would need to reduce the production of CO2 by, I think, 51% in the next 2 years, in order to really decrease the amount of the damage that we've actually created. But that won't be possible. And although, thanks to I'm sorry to say that, but thanks to the pandemic and the 2 years of what was it? 2 years of limited transportation. What was it, like 2 years of
reclusion?
Lockdown.
Of what? What happened? Okay.
We spoke at the same time. I
go
just said
ahead,
reclusion,
sorry.
but probably you have a better word.
Oh no,
Yeah.
I wanted to say lockdown, just that. So.
Oh, thank you. I was going for the lockdown. Thank you. So going back to, thanks to the pandemic, at least this one of the positive side effects has been the lockdown, and it has limited a lot of quite a substantial amount of CO2 production, but that's not enough. And we, in addition to limiting the carbon dioxide production, we would need to capture it from the atmosphere, and there's no method, there is no technique yet developed yet, and the problem here is, like, what I was asking before was I was asking about if you theoretically replaced all the current fossil fuel with, as you mentioned before, it wouldn't be possible for transportation, like for like ships and other types of transportation. But if you could replace with a renewable energy, which does not produce CO2, I was wondering, or at least part of it with nuclear power plants, how would that, what would be the impact in, I don't know, the next 5 years? Would that help with the plan, the Paris target, for instance, to reduce by 51% of how would you?
I mean, there's no question about this. Of course, it would help. I mean, if you just look at the composition of energy production in Europe, coal and gas, it's still majority. It's still used as a majority resource in many countries, like in Poland, for example. So if you can cut this, it's bringing us closer to the goal very much. So yeah, we should do it. I mean, it's not possible because of the political climate, and also because it takes a lot of time to build nuclear reactors, at least the big ones that we are building right now. There is a push towards something called SMRs, which are basically small modular reactors. The idea here is that you could produce them faster and cheaper. And because they are small, so they're also much easier to manage, and the potential fallout of a catastrophe would be much smaller, much more limited. So they have a lot of promise, and there's extensive research going into that. And you know, there are prototypes, I think, already established by Westinghouse, I want to say, one of the big players in States. So they will go into operation in the next few years. If they are successful, then you know we could start implementing them all around, which would be a good alternative to the big reactors that are dominating the market right now.
Maybe if we change, that's like kind of a personal anecdote. If we switch to nano power plants, I think that they may be more accepted.
Perhaps, right? Because they're smaller, so.
No, I was thinking more about the terminology.
Actually, yeah, there's a minimum size that a power plant can have.
I guess you should just consider the cost versus the energy output that you're going to get out of it. And at some point, it just becomes impractical, right? You need to withstand some sort of pressures that the reactor is going to operate on. So this limits how thin your walls could get, for example. And I mean, I guess you wouldn't want to have a nuclear reactor in every house, right? Because then the multiplicative factor of the amount of them and what people can do wrong with them, or you know, just imagine what happens is that the house crashes into your car crashes into your house and hits the nuclear reactor. I mean, you don't want to have those options. So we need to find the right balance, like have a reactor of a size that's significant enough to power a neighborhood or a city, right? But you know, still manageable and easy to produce and cheap.
So interesting. I have so many random questions.
Sure, go ahead.
Can I ask a couple of random questions? I just imagine like these nuclear submarines, right?
Yeah.
When they become like obsolete, the structure, but not the nuclear device. Can you use them to power, like, can you put them on land and use them to light a city, for example?
I guess so. I mean, they will be probably utilized for as long as they can. So afterwards, your reactor will be like 50, 60 years old. So maybe you want to retire it. It's already done its job. Let's look into building a new one. Materials just degrade over time. And like there was a case, there's still a case right now in Switzerland in one of the power plants, which is pretty old, I think 40 plus years. They found some structural damage in the reactor pressure vessel. So the big tank that's basically holding all the nuclear fuel. And they spent a lot of time to investigate, are those faults developing over time? Have they been there since the production of the vessel? It's pretty well known that radiation is degrading the material, so it's losing strength, right? And at some point, the only thing you could do would be to, for example, replace the whole vessel, which is extremely costly, just doesn't make sense. It's better to build a new one and process the old ones.
I have a second random question, and that's all.
Sure.
I mean, this one is closer to my home because in Chile, there were some conversations about having nuclear power plants until Fukushima happened. And that was a big earthquake, right? And Chile has a lot of earthquakes. So after that, nobody else talked ever again about nuclear power plants. So, I mean, what happened in Fukushima? And can it be done safe for places in which you have like a probability of big earthquakes?
Yes. I mean, what happened in Fukushima mostly was, maybe let's go to the beginning. So what happens is you have a reactor that's producing a lot of heat. And then as a later stage, you're converting this heat into mechanical power and then into electricity. That's the basic conversion chain. So what happens is you can turn off the reactor, but it's not like a light bulb. So you turn it off, but the reaction is still proceeding at a much, much slower rate, right? So the device is still producing small amount of heat, and you have to cool it down. Because if you don't, the heat accumulates, the temperature is increasing continuously, and then it melts. The fuel can melt, the vessel can be destroyed. You have a very hot material, so a lot of stuff is going on. So in Fukushima, what they had is they had those diesel engines that were operating pumps. And the pumps are used to circulate the coolant to remove the excess energy after the reactor shutdown. Then the tsunami wave came, the diesel generators were submerged and they couldn't provide the electricity. So the whole disaster then progressed. But there are new designs of reactors that they are not depending on the active cooling. They are all passive. So even if the energy is cut from the outside, the reactor will shut down gracefully. And there are numerous ways to do this. Going to this is not relevant, but the takeaway point here is that even if the worst thing happens, the reactor will shut down and the residual heat will be managed. So it's safe. And as a next, because the nuclear safety takes this philosophy of multiple barriers, right? So first, you want to avoid the whole thing. But if it happens, then you have the passive cooling. But if this is not enough, then you have another barrier. So for example, there was this Russian design for a vessel located underneath the nuclear reactor. And let's say you have the worst case, your fuel melts, right? So you have this radioactive magma. And what happens is it just flows into this device, which is called the core catcher, right? So it's catching the core.
Cool name.
It's filled with some special bricks. The bricks are melting, mixing with the radioactive magma, dispersing the radioactive material. So the reaction rate is going down, and it's so large that it can just contain everything inside. So you have another layer of defense of a passive system that can protect this. And this is this philosophy that you're doing multiple steps. So redundancies, I guess, is the answer. Right, but if Chile, I don't know the particular amount of earthquakes you're getting and how strong they are. are there regions that are less volatile than others? And I would still try to locate the nuclear reactor in the safest place possible, right?
All Chile is active.
All Chile.
Yes. I mean, probably not very close to the ocean.
Okay. So, yeah. I mean, I can't give you the definitive answer, but it might be that then this energy is not the most suitable one. But I mean, maybe you could place them farther away in neighboring countries and just transport the electricity through the grid. I assume it exists, so the countries are interconnected, like in Europe.
Not really.
No,
in Chile,
really.
You have the Cordillera de los Andes, this big chain of mountains. It's huge, it's massive. So I don't think that actually could work. I mean, I think there were some, I'm speculating because I don't remember exactly, but I think there is some gas ducts, how is it called in English? I don't know, that are between Argentina and Chile, or there were conversations of having one, and then that.
Oh, you mean tunnels?
Yeah, tunnels. I mean, gas tunnels. I think because Argentina has gas. Yeah, I don't know if that can be used for. I mean, I would say if Japan could handle it, except for the part of the tsunami, I think Chile could. And if the technology is better and the safety is much more improved. I mean, I just see political fears, of trying such a thing, knowing the case of Fukushima.
I mean, it's reasonable. It's good that people are afraid because it's not something trivial, and we should be afraid. I mean, maybe not scared. We should be respectful of this because there is possibility of issues. So it's actually very good that this approach to safety is really thorough. So I guess to sum up, I'm not sure if the nuclear reactors are the best solution for Chile in particular, but it should be investigated. And probably there are some studies done already, right?
I'm not the right scientist to ask.
Okay. Well, I mean, we would have to turn to Google and then we can find out. But
I just remember there were some conversations, and after Fukushima, they were stopped forever or for a long time.
Yeah, actually, it was personally for me, it was the same. I started my PhD a year before Fukushima.
No.
Yes, the project was quite large. We had a lot of funding from public and private partners. And Fukushima happened, and then from day 1 to day 2, the funding just disappeared. So we had to rethink everything, right? So yeah, I mean, it's not as big as an impact of not building a power plant for Chile, but for my life, it had a big impact. Yeah. So I understand, yeah.
Talk about Fukushima with the switch, because maybe that triggered also that switch.
I mean, no, I still, finished my PhD in the nuclear safety, but then when I was looking for a postdoc position, just another opportunity rose up, and not directly tied to nuclear safety research. So you had to take it, or I had to take it if I wanted to stay in academia.
But so when you started your journey at some point, right? I mean, you made some choices, something triggered your choices. How did your journey start?
I mean, how far back do you want me to go? Where is
not till when you learned to speak and your parents taught you.
Sure.
No. Why did you choose physics at all? What triggered your choice?
My memories go back to this show on Cartoon Network that I was watching as a kid called Dexter Laboratory.
Oh,
and the main character is like a small scientist kid with a big secret laboratory. So I don't know, maybe this was something that planted the idea in my head. And then as years progressed, I was reasonably good at school and I enjoyed physics, mathematics. And at some point comes the step that you have to make the decision which subject are you going to study. So I was torn between, I'm sorry, there's a flyer down here and just so annoying. So in any case, I was stuck on a choice between astronomy and mechanical engineering. And, astronomy is maybe not the most profitable field. So I got convinced by my parents to go into mechanical engineering, which it got me where I am right now. So I'm not sad about this, but I'm sometimes wondering what would have happened if I actually went with the maybe more wild card choice. So yeah, I mean, I studied mechanical engineering and I just somehow knew I want to do a PhD. So I was looking for a good place to do that. ETH, the school in Zurich, I think was listed on one of the rankings as the best technical university in Europe. So I thought, okay, if I want to do a PhD, why not there? So I started applying, and it wasn't easy to get in at all. I think I got through the side door because I found an ad for an internship. And so I started at ETH as an intern doing computational physics. And after a couple of months, I guess my group leader was happy enough with me to offer me the PhD position. So, I found a way. And from there, it's just, couple more years. And after PhD, you're faced with another decision, right? Are you going into industry? Are you going to do a postdoc? If you're going to do a postdoc, then where? So in my case, I actually took a lot of time to finish my doctorate. And in the last 2 years, I was in parallel, I was actually working as a mechanical engineer, so I was finishing my doctorate as after work, which I don't recommend. If you can, just do it on time. Don't try to mix the two. It wasn't. I didn't have a lot of free time at that period. So in any case, at some point, an opportunity arose to do a postdoc. I was actually asked by my old thesis supervisor that there's this position in Luxembourg. Would I be interested? So I applied for it. I went for an interview and it went well. The field was also very appropriate to my background. And I thought, okay, why not? And as I said, it was not so far away from Switzerland. So the family life can be agreed with it somehow.
So it's about choices.
Sorry?
It's about choices. So you have to make a choice at some point, and it's never trivial. I mean, for most of us at least.
But it's not like it's a completely free choice. You're always constrained by the opportunities that come your way. I never thought I'm gonna do research in nuclear safety. And it was just, I was in the right place at the right time, and I snatched this opportunity.
So my question now, can you tell us more about your success story? And you chose your journey, and what were the challenges that you faced during your journey?
I'm still struggling. Continuously.
So I guess the anxiety and the stress is slightly lower compared to an initial stage when during your learning curve, when you're still learning, you're still like inexperienced and very probably scared, and then you don't really know how to deal with challenges at first. Did you ever fail, and how did you fail? Or what did you fail at?
Yeah. Because rather than telling a successful story, sometimes it's just better to tell the unsuccessful stories, because people always are telling, I made it, you can make it too. And they talk about the process, but I think you can be very, very unsuccessful. And that's a path. You require at least one chance to be successful. In the sense, like, I have failed so many times. I have misunderstand so many times that I keep trying. After my PhD, I applied for many positions, like all around the globe, and I got second in quite a few. I didn't even get selected in so many others, and it's very, very frustrating. And this is the same with science. You're trying paths that you never know where they lead to, and at the very end, what made me successful, or like maybe one sufficient success in order to keep going, was to keep trying. That's it, and to keep trying, you have to really deal with frustration. You have to understand yourself, and you have to be clear that if you want to keep trying, you have to enjoy the ride. So I will keep trying as long as I enjoy doing science. And there are many things which I do not like, many things that stress me. I'm still struggling, to have a routine, especially because I always feel different, and I haven't been diagnosed, but I'm taking medications through a psychiatrist for ADHD, as we have discussed with Jocelyne many times. So I'm too spread out. For me, it's sometimes very hard to focus, and the medication that I'm taking helps me to like focus myself, and also helps me to find a place which I call work, to have a routine, you know, and to keep trying. Having this routine helps me to keep trying until I reach the level in which I understand enough to make myself the right questions.
I guess actually that having a routine in a case of ADHD, it's very challenging, and it costs a lot of energy.
I have discussed with a psychiatrist. She told me that very likely I do have ADHD. It's just like to get the proper diagnosis requires some testing. You know, that is a questionnaire, a survey that you do. It takes months to get even just a schedule to do it. Yeah, so I'm not diagnosed. I'm just being told that I very likely have that condition, and I'm trying this pill to see if it works, and it actually works. I mean,
so if it works,
it helps. Yeah, it's like for me, I feel like many times I deviate from whatever thing I do because I'm kind of addicted to instant gratification, and mean cell phone, mean anything, you know, many things. So when something is like there's a slight obstacle, it can be very simple, you know, but the stress that that causes because I cannot focus on it, you know, it makes me want to deviate immediately from that and look for that instant gratification. So I procrastinate. So I tend to procrastinate a lot. When I do, I mean, I kind of save it by procrastinating things that are still useful. So I do a lot of stuff, and they are kind of useful, and at the very end actually help me to reach somehow the goal that I'm trying to reach, right? But many times can become very chaotic. So with what I feel when I'm taking this pill is like this obstacle that seems like a huge wall that makes me want to jump away from whatever I'm trying to do. It's suddenly not so tall, so I can jump it, or I can just walk it past through it. So and it's the only way I can describe it, because it's a very subtle effect. I'm still like taking it for just a few months. I think it's working. I have to see, you know, it's like my personal journey. I know that every person is different. I know that a lot of people probably identify with the struggle I'm just describing, because probably many people have ADHD and don't know. It's very underdiagnosed probably, especially in women. And everybody deviates. I mean, many people procrastinate. It's like a normal human thing. And we live in a world in which efficiency is very valued. And sometimes that generates a lot of anxiety and stress. And yeah, I mean, sometimes procrastinate is when it's excess, it's a bad thing, but it's also a good thing because it, as we discussed before, liberates your mind, makes you explore new paths. And that kind of creativity actually also helps to find new ways to solve problems. So it's not a bad thing. It's just like you have to find the balance, and you have to understand how you work. There's many people in my field that are very different than I am. And I feel like I'm like I feel different. I don't know. Maybe everybody's the same, and we just don't talk about it. But for sure, there's a lot of diversity in the way we do science, and we have to appreciate that. So my way of being also contributes something, you know. Yes. How much or how less, it's also, I mean, debatable, you know, maybe measurable. But the thing is, diversity in general should be valued because it brings different paths to understand. And that's what science is about. So I'm a huge advocate for diversity in science and in life in general, of course. Mm-hmm.
So a few words, because as you mentioned, so you haven't been diagnosed, but you have to go through a test, which is very challenging, especially if you've got ADHD, because you have to focus on something that you don't necessarily care about. Mm-hmm. And I did it, and I was just recently. So I've gone underdiagnosed for many years, and it's been really, I mean, I had to find like self-help methods, and it wasn't easy, and it wasn't like trivial to find help, but I was also lucky enough to find like support and the right people who gave me like at least, you know, the right advice at the time. So I was able to cope to some extent without any medication and without any therapy. And so being diagnosed with ADHD and ASD, so autism spectrum disorder, which with the light side, so the light part is called Asperger's syndrome, so it's obsolete term, not medical anymore for that, which is high functioning autism. So it doesn't look like it, doesn't feel like it at the beginning, so you just see like the side effects. And ADHD also doesn't necessarily it's not evident. It's not like you know, to someone who's really depressed or who's got like some different mental condition that you see it's a completely different person. Like it looks more, ADHD and ASD, by the way, it's more like it almost looks like personality, almost like a personality trait. So you don't feel it, you just feel the side effects, and you think at the beginning it's just like, I'm very insecure, I've got anxiety issues because everyone has, etc. And okay, you can argue that in physics we are all on a spectrum, so we are kind of almost converging, but there is still side effects which appear with different magnitudes, and some of them can be very destructive. So I suffered from test anxiety disorders, which is related. It's like one of the side effects of ADHD, but autism as well. And it was very difficult at the beginning to understand what's going on. And I thought that it's normal, that everyone deals with, for instance, exams the way I do, that you can't sleep, you can't even almost drink water. But there are people who actually don't speak about it because it's a very gray area. It's a very it's not even a matter of being taboo, but it's not very, people are not aware of it. It's not a known field in psychology. There's still like, it's a developing field, so it's not very exact. It's not an exact science, so it's very difficult. There, of course, you can argue that every diagnosis it's relative, but there is some cutoff that you reach past, which you can state like almost in a binary way, you've got ADHD or you've got ASD, rather than you don't have it. So you pass the cutoff and you're there. The issue is how can we help people, support them to at least help themselves. With the case in the case of ADHD, you mentioned there is this medication which is a central nervous system stimulant. So and it's called Ritalin. So there is Concerta as well, the different long-lasting version of it. But Ritalin is very effective at helping with focus, and it's a paradoxical situation because in people with ADHD, it doesn't necessarily trigger euphoric states, but rather it calms them down and it allows to focus in a calmer way on more things in an homogeneous way, rather than just being hyperactive and completely like selective in terms of selective attention. So and there is a deficit in all other aspects the field, which is very destructive because you end up having students who are potentially very good, but they're just constrained by some manageable conditions which just require some fine tuning. And the problem with sorting this out, with solving this problem, is that first of all, it's very difficult to it's very difficult to bring up this topic because it's it's still a medical issue. So usually medical issues are pretty private. So you, as a professor, as a supervisor, you can't just go up to someone and say, I think that you may be autistic, or you may have ADHD, or maybe bipolar, because you can be sued for that, understandably. And not everyone can accept that not everyone actually accepts that there are diagnoses. Not everyone admits to them. So there has to be both sides, so both students and professors or supervisors who understand, and we need to raise awareness and understand that this is a potential issue, but also potentially manageable if the right advice and support is given. But at the same time, there has to be also some openness. So you have to be open to discuss about it and be aware of the fact that not everyone wants to hear that they need help. The best thing that a student can do is at least seek advice and see therapy, or at least coaching, because there are people at university who provide coaching even for free, and try to speak, to people, like, say, describe the amount of stress they're going through, the anxiety that they're going through, the depression that they're going through, and how to deal with it, and just be open about it, and stop ignoring and being, too proud to accept that there can be a condition that has to be dealt with. On the other hand, professors, supervisors, and managers, whatever type of equivalent to a manager, they have to drop the bias. Like, they have to stop judging a student. They have to be more open about their profile. If they see that there is a student who's got like a lottery almost, there's some topics he's very good at, but really good, and some other topics it looks like he's a complete idiot. That means something. That's a clear proof that something is going on. And this is not laziness, this is not lack of skills, this is probably something that can be fine-tuned. You have to address that issue. So I overcame the failures a little bit. Like, I stopped caring about getting everything perfect. So I accepted that maybe I wasn't going to get there were subjects that I was less inclined to and less interested in. So I thought, okay, I'm not going to have the best grades, average, the best grades at everything. So I accepted and I moved on. It hurt, of course, but I had to get over it when needed. What about your success story, Filip?
Oh, yeah, I think it's very nice of you to assume I have one, but no, I mean, I guess.
Story.
Of course, I consider myself graduating as a sort of a success, because there were points when I wasn't sure that it's going to happen. It's, I guess, something that nobody tells you before you start your PhD is that it will be at times extremely frustrating. Things will not go your way. And as Sofia mentioned, procrastination is just so powerful. When I was writing my thesis, I think my apartment was never as clean, So yeah, I was doing useful stuff, just not the stuff I was supposed to. I think if you want to pursue a career in science, you have to be very persistent, to be able to push through the times when the things are not going your way. But also there's a lot of tools that can be utilized that are just not, I think, properly shown to students, like project management, like proper planning. This is something that is, I feel like, treated without sufficient, detail, because it's very useful. Yes, doing science is amazing. It's about discovery. It's about creativity. It's about those breakthrough moments when you have the idea, but that's not all of it. A lot of it is just doing mundane research, going every day into the lab, trying to fix the stuff that's not working. Sorry?
Stagnating at times, and you have
Stagnating, of course, going back, throwing away a lot of time, maybe, because the experiment didn't work. And in those cases, the code didn't work, or maybe it wasn't useful at all.
The equations,
exactly.
The equations
bugs are everywhere. I mean, people that doesn't program should know that bugs are the most nasty things we can have, and we have to deal with them all the time.
Exactly. So you need to have this persistence, and it's great if your supervisor is providing the support. And of course, as you both said, there are different ways in which science can be done. So it would be great that students are just shown an array of tools that they can utilize, because for somebody, maybe they don't need to have a plan. They are very good at doing things on the spot. For other people, maybe laying out the detailed schedule of their day or of their week is the best approach. So making those tools available would be very useful. And so coming back to the success story, I think I consider myself graduating as a success despite the obstacles. And it wasn't easy, but I'm happy that it happened.
You found a way to, at least both of you, at some point, to coach yourselves. Or in my case, I didn't want to find an excuse. I wanted to find a way. So I wanted to graduate. I wanted to do theoretical physics. I looked for people who gave me the inputs to know what I should do in order to find the best possible way to achieve it.
So I just wanted to say that you shouldn't also forget about taking breaks and take your holidays, regenerate, because if you just focus on work for a couple of years, you're going to burn out. Take your vacations.
Breaks. I understood pills.
No. I mean, if you need, yes, pills, of course. But I meant the breaks. Give yourself some time to breathe.
What helped me was, because I'm pretty much of an introvert. I'm like very introverted. So I need to be isolated. I like to speak to the right people and a few people, like one-on-one, whenever possible, but and share my ideas and thoughts and build them. Interesting exchanges, but I can't stay among people, and I'm not even socially, I don't have social skills, by the way. So I usually spend a lot of time on my own, and I kind of have this one-way dialogues with the big minds who are not alive anymore. Philosophers, scientists, and I watch a lot of videos on YouTube available on the interweb. All these precious information and precious teachings that these people left, to us. They are basically talking to us. If you read like the quotes that the biggest minds, the biggest philosophers and scientists left to us, there is no better coach actually to tell you what exactly you should be doing, how you should plan your life. It's all available. So, okay, success story. We've got success stories in science as well. There are a lot of failures and overcoming of these failures, stagnations, string theory, quantum gravity, big question mark. Something many of us are obsessed with, myself included. Sofia, so as an astrophysicist, you share a lot of interesting topics. One of them being exoplanets, and the other one about the James Webb telescope, one of the biggest achievements in the history of humanity, I think. And so I'm pretty sure that you the beautiful earrings and got a lot of information to share. So the James Webb telescope, which is a topic that I love, and it's amazing. I mean, it's been the advancement basically of science in a direction which is like beautiful, and it's going pretty well. And I wanted to mention how it got there, the Lagrange L2 point and the gravitationally stable point orbiting around, because many people don't know actually where this telescope is orbiting, where it's gone actually to. And the fact that you mentioned exoplanets, that's an interesting topic, but I wanted to just mention, like many YouTubers do, probably just for like a clickbait or for likes, I don't know. When you read headlines like a James Webb telescope is going to look for life 2.0, it's misleading information, and it's not necessarily the main goal of this telescope and this mission. So the mission is to study the early universe. It's a big collaboration. It's like hundreds of universities and institutions are working on it. So it's also in terms of funding, it's very difficult to invest, to find the fundings for anything in science. And that's another a different topic, but another issue in academia. So they launched it on December 25th, 2021. And the aim was to probe the cosmos and to uncover basically to understand the history of the universe. So the very beginning, detect like the different composition of the atmosphere of some exoplanets from a perspective of understanding how our planets formed. We are interested in knowing if there is somewhere form of intelligent life somewhere in our galaxy or somewhere in the universe. And we can also account for the Fermi paradox. You know, they're probably not going to make any contact with us, reach out to, I wouldn't reach out to us anyway if I was away, but that's a different story. So we want to understand how the universe, what happened after a assumed Big Bang, how was the initial conditions of the universe. And we've got ways of measuring, observing different aspects of it. So there are different tasks the James Webb telescope was built for. And so you shared today the deep field that has been imaged by the James Webb telescope, and before that there was the Hubble telescope, which was the one orbiting and then giving us this beautiful images and the information about the cosmos. The James Webb did it in, I think, was it like, if I'm not wrong, correct me if I'm wrong, in a few hours, whereas the Hubble telescope, it took like a few days.
I don't know exactly how long it took, but what they said is like they took it over breakfast, kind of. And that's what they said. This image that you're seeing in the background, that's what they said. It's like the deep image from James Webb, and it's nothing compared to how long it took for the Hubble to reach that image.
Right. So it's like if you took a grain of sand, so if to the sky at this length, so the arm length, let's say, right? So that's the bit, or it's called this peck of size of the James Webb's view, right?
Yes.
So
exactly.
that's the galaxies which you can find within that size, right? Which
wait.
Yeah, they're not very representative in terms of size,
right? I have like a green screen in the background, and I
right.
did by moving myself.
That's brilliant. You disappeared for a few minutes, and then you came back with a green screen.
Yeah, but I moved the thing, so now I have to move the
and that's pretty big. So it's not even.
Wait,
we're talking about sizes, and that's not even representative in terms of sizes. It's too big. So yeah, it's very, very, very tiny. I mean, it's literally a grain of sand, right? Containing that type, I mean, in terms of sizes, that the galaxies, I mean, there are a fraction of galaxies, and the light that is coming from them, some of them, has been traveling billion of years. So that tells us a little bit about the beginning of the universe, right?
Saying one of these galaxies is like 13 billion years away, or something like that.
So exactly. So it means like we are basically looking back in the history of the universe, and that's beautiful because I
mean, in time, yes, we are looking 13 billion years back.
Well, by the way, in astronomy, you measure it as a redshift. So you say at redshift Z, it's defined as Z0.
I have no idea of the redshift of this galaxy, but it's probably very, very far away, like 11, and that's huge.
Just to mention, so at redshift Z equals 0. So that's defined as now. So now, at the moment, we're at redshift 0.
And
right?
redshift measures the expansion rate of the universe. So the farther away you look, the fastest things move away from you, and you can measure that. And that gives you a number that you can quote, and it tells you a distance from you and also a time, because the farther you look, the farther in time you look, because the light takes time to arrive.
So they're pretty far away. So they're pretty old and distant and old, and it's like looking back in time. And so it's basically one of the greatest achievements it has been already shown by the Hubble telescope, but the resolution here is not comparable. I mean, it's much better.
It's not only the resolution, but also the wavelength range that is So these telescopes is in the infrared wavelength, so a much redder color than what Hubble did, and that has several advantages, especially because of the redshift. The things that are farther away from us look redder than the things that are closer to us. So having access to a redder wavelength range with this telescope let us have access to an earlier time of the universe. And that's what they were saying, that this James Webb is going to revolutionize our understanding of the early universe, because we are starting to have access with great depth and with great resolution to an epoch that was not accessible from Hubble, because of it didn't have the wavelength coverage that James Webb has.
And that's one of the tasks actually was built for.
Exactly. And actually exoplanets were something that they were actually mentioned in this press release, that at the beginning we didn't know that there were so many exoplanets around. We didn't know how many planets were around stars, and we figured out that there were like so many. I mean, we don't even know, maybe all of the stars have some kind of planets orbiting around them. And so the possibilities are so vast, right? How many of those may have conditions that can sustain a life that the one that we know of, right? I mean, who knows? Maybe there are other ways of having life that doesn't imply to have carbon or water, you know? But at least we can try to look for things that look like us. And they were mentioning that one of these images released in this early release of James Webb was a spectra of an exoplanet that they found water, also clouds and haze in that planet, evidence for that. That's fantastic. I mean, imagine that. Imagine the possibilities. Maybe we could even go there as humanity and live in that planet. We have water.
Some even claimed, that's a little digression, some even claimed that on Mars there are structures which hint at, because we've received one of the latest pictures of, was it Perseverance? Which one? Curiosity, I think, died.
Mm-hmm. I don't remember the exact name, but they found evidence for water. There is water. I think there was an image years ago that looked like some kind of Egyptian thing, but I mean, that was, I mean, it was random chance. It just looked funny, you know. I mean, when you have so many random patterns, there are some things that may look like some kind of structure, but you have to be very careful as a scientist, because sometimes your eyes trick you. You are trained to look at patterns, right? So that pattern looked very like something human-made or like intelligent-made, but actually it was part of a random chance of having that shape. And better images apparently show that it was like nothing. Yeah.
So back to the James Webb telescope. So it's worth mentioning that when you said, so there are two types of lovely earrings. There are two concepts. When we talk about life, most people are interested in knowing, in trying to find intelligent life, you know, so the intelligent life requires a habitable zone. So the planet has to have
liquid water on the surface.
Equivalent conditions, exactly, to have liquid water, at least the way we know life on our planet. If it's meant to be intelligent life, our concept is at least like us. At least like organic chemistry, so made of carbon molecules and well-defined structures, molecules which need to have the same conditions that we do, or at least equal, equivalent conditions. But there may be hints of different type of maybe less intelligent life. And we're interested in that as well, because if there's whatever type of even primitive organism on any exoplanet that we can discover, that may hint at potentially very interesting information about ourselves and our life as well, because we want to understand, first of all, we want to understand what are the conditions that drive the creation of life. We don't even know how we came up from what type of evolutionary, I mean, the very primitive, the primordial life. So what was it exactly? We can theorize it, but we do not have any evidence of what it was at the very beginning.
And they were showing like a spectra of a planet, exoplanet, and they detected water and clouds on the planet as the most like the best spectra ever taken to an exoplanet.
So
it's just stupid. It's amazing. I have goosebumps. I was looking at the things and I'm getting goosebumps.
That's why this is interesting, and also the fact that we want to understand, because by understanding the beginning of the universe, we can understand the initial conditions, so we can understand more about the current structure and like large scale, and maybe understand better also topics like gravity. So I guess that could help, and because we of course we do not understand the main problem is that we do not understand gravity at the quantum level. So as opposed to the other forces and particles, or if you want, we don't even talk about particles. Usually you talk about fields, but just to be more general, we're made of fields. The most beautiful theory describing almost everything, and with the most rubbish name, which is the Standard Model. It describes pretty much everything besides gravity. So we do not know what gravity is at the microscopic, so the quantum level. We know Einstein described it, and we have equations describing it as a curvature of space-time as an effect of mass and energy. But we do not know a lot about the universe and what we're made of. So we hope that if we, with the information, with what we can observe with the James Webb telescope, that we can actually understand maybe also the gravitational lens. Actually, you can see the gravitational lensing in the James Webb, in the deep field image.
You have a cluster of galaxies in front of you, and behind that, there's more galaxies that are much farther away than you. And because of gravity curves space, and this structure, this galaxy cluster is so massive that the light that is passing through that cluster is bended like in a magnifying glass. It's like exactly the same effect. So galaxies that are in the background of this cluster are bended and have these like very funny shapes, and they look curved. Okay, so that these gravitational lenses actually trace matter. And what matter, right? So you say you have like what we call baryonic matter, what we are made of, that which is basically matter that interacts with light, and we have this dark matter which apparently doesn't interact with light, and it's most of it, and we can trace that. And so if we can model properly, and maybe with James Webb we can do it much better, how these gravitational lenses behave around matter, maybe we can understand better what that matter is. If it's actually something, a particle that we don't know yet what it is, or it's actually some kind of modified version of gravity than the one we know of. And that's basically it. Yeah.
So there is a theory that it's not necessarily matter, but we have to define the different like laws of physics in that term, like gravitation, modified gravity, which would be just a simple physics effect of a different phenomenon going on, not necessarily particles, because many experiments have been, and many particles candidates for dark matter have been theorized, but none of them has been observed or confirmed.
I don't know what Filip thinks about it from like a physics perspective.
Yeah, I'm not sure I can actually contribute much because, I mean, yeah, this is a little bit different scale of things that we're talking about, right? The size of the structures that you're considering, that James Webb telescope is considering. I mean, this is way off, right? This is the macro scale. Nuclear physics is more about the micro scale. And of course, there is some, like one is emerging from the other, but we are seeing that there are very different laws that govern the behavior of the two. So like gravity is a strong force at the scale of the universe, but it's extremely weak force on the nuclear scale, right? So I enjoy reading about this, but it's not my bread and butter.
But it's still, nevertheless, it's very fascinating to.
It is, yeah.
Quantum gravity, right? The ultimate field to be discovered, right?
Like
one of the ultimates. Quantum gravity.
Please. So,
yeah, I mean, and you as a nuclear physicist, right? Stars are basically nuclear reactors of fission rather than fission, right? And also, I mean, the beginning of the universe apparently was very similar to the conditions of the interiors of stars, and
oh yeah, I think even much more
from that, right? Yeah.
Well, one of another interesting topic, which is actually a different telescope. This time is the Event Horizon Telescope. So it's a AHT, which looks almost like ETH. So sometimes at the beginning,
I confused you.
I said AHT. Someone misspelled the name of.
And it's funny because it's not like a telescope. It's like a combination of a consortium of telescopes that are combined in a very smart, sophisticated way that I don't understand to create one single image. Yeah,
exactly. And
well, a model of images, actually. The image that you see of the black hole is not like a real picture. It's just like a combination of a model of how the image should look like based on certain physical conditions and possible solutions. So that was one of the solutions to the observations that give an image that looks like a black hole. And there are several,
They had to take a lot of data in the proximity.
So it's like it's remarkable from like a data science perspective.
Exactly. And the problem with the first, it's worth mentioning that it's M87. So M stands for Messier's objects, right? So
are you talking about the first picture, right? Yes. About
the first was the very first black hole, and it's one of the largest known black holes. And well, it's got a mass of 6.5 billion times the mass of the sun, our star. At the center of every galaxy, there is a supermassive black hole, and the galaxy orbits basically around it, right? So,
I mean, everything rotates through the center of mass, and the black hole happens to be at the center.
Yeah, exactly. Digression again. It's like when you say that the Earth orbits around the sun. It's not exactly orbiting around the sun. It's actually the Earth and the sun are orbiting around the center of mass.
And the center of mass, I think, is very close to what we define as the surface of the sun.
I'm not sure if it's a few thousand kilometers.
I think it's actually very close to the surface of the sun. That's what I remember. Perfect. I'm not sure. I mean, I'm just quoting from my mind, so please take it with a grain of salt.
So it's still within the sun, but it's further away from the core of the sun. So it's worth mentioning it. But it's just like but that's because this is the physics behind this rotations and the fact that we've got like supermassive black holes at the center of every galaxy. And so I was puzzled, like M87, why not our black hole? So it's
I can tell you the answer because I asked myself the same question when this image.
I know it.
Yeah. Well, if you know it, I mean, it's because it's much more massive and farther away. So it's like easier to see the forest, kind of. And also because it's more massive, it rotates. It changes much slower, so it's easier to take a picture. The one in our galactic center is just 4 million times the mass of the sun, so it's it changed its look much faster. So you really need to be much more careful to get a right picture.
So being more massive, it allows, as you said, the speed, the velocity was much less.
It's basically like the velocity of whatever is orbiting around the black hole, like the gas.
Yeah, that's substance.
Yeah.
It's basically gas. There's this matter surrounding, because that's the one emitting light. There's no black hole emits light of its own.
We want to take a picture of the shadow, basically.
Yeah, and around, so basically it's the material moving around the event horizon. So this is the boundary of the black hole region of space-time around the black hole. And the point is that it was very difficult to collect the data of our black hole. So it's, by the way, it's called Sagittarius A, right? That's
Sagittarius A star. Yes,
A star. Yeah,
of the center of our Milky Way.
Yeah, so M87 star, it's the black hole that's been observed, and it's in.
I guess so. Yeah, I didn't know. Yeah.
M87 galaxy, so which is far away, by the way, but while the M87 is 0.5 billion times our sun, our black hole is just 4 million times. So it's 6.5 billion times our sun, 4 million times Sagittarius A star. It's 4 million.
Yeah, but it's
times.
like 10 times. I mean, it's like 10 times, kind of 10 times more massive, but also 10 times farther away. So they are kind of the same size when you look at them.
But
besides that, there's another problem, right? With our the center. I mean, we are in the plane, of the galaxy disk. So we're looking at this galactic center through a lot of things. So also there's like this problem of disentangling whatever is foreground with respect to the black hole.
Foreground, yeah.
Yeah. And then you said M87. I don't remember exactly, but it's not exactly edge on, right? So it's like looking at us, so you can see much easier the black hole. Yeah.
So it requires also less effort. So that was the point. And it was a very puzzling question for me at the beginning. So I did some research and I realized that there is actually an answer to that.
There's these supermassive black holes in many galaxies. And for example, the ones we have in our Milky Way, it's very passive. So it's not interacting too much with the gas around it. But there are several galaxies which are strongly interacting with the gas around them in such a way that they heat up the gas and release energy in a collimated way, like a laser, like normal to the plane of the galaxy. And we call these objects quasars. And they're so powerful that actually not only illuminate our view, but illuminate everything that is around them. So part of the science we were doing at ETH with my PhD, and you, Jocelyne, may know a little bit of that too, we use these quasars as flashlights to find out the structures beyond galaxies, what we call the cosmic web. The halos around galaxies, we call it circumgalactic medium, or the filaments in the large-scale structure that connect galaxies that we call the intergalactic medium. So during our PhD, we were taking one of the very first images of this gas around the galaxies, and we do it through an emission line called Lyman alpha, which is just a recombination line of the hydrogen to the ground state. And it's the most powerful line, but also it's very resonant. So it interacts immediately with the gas around it and bounces many times. It's like scatters everywhere. So you don't know exactly where the light comes from. And we want to know exactly that. So we want to trace also the structures that we see in other lines which do not resonate so much. So one of the things we got time for in our team with the James Webb is to trace those structures in another emission line, which is called H alpha. So it's another transition of the hydrogen, and that line is not resonant, so we can trace exactly where the light comes from, where the structures are, and we can understand a bit more of the interconnection between what happens in the galaxies and what happens outside galaxies. So that's something I'm very excited about. I think it's remarkable, and maybe you Philip can say more about it, like how when we are studying these large things, very, very far away in magnitudes that are impossible to understand in the human mind, right? Dimensions that we don't grasp. But we need the physics that happens in laboratories, or people that study like particle physics or fundamental physics like you do, to understand those structures. So it's like something that is very, very many orders of magnitude larger than us needs physics that is like many, many, many orders of magnitude smaller than us.
Oh yeah, I mean, you're completely right. It's just about this emergence, right? That you put a lot of small stuff together, right? We know the physics that's governing the small stuff to some extent, and new stuff is created, right? And sometimes it's surprising. Like you can't predict the properties of the large structure just by seeing the tiny elements. So, as you're saying, you need to know how the quantum world behaves, how the thermodynamics laws can be applied to the basic matter. But from this emerges a whole new world. So there are connections between our fields, but there are still very many different specifics, right? So yeah, we're studying the same stuff, but we have a different size of magnifying glass.
That's definitely, as you said, they both combine, and by understanding of, the physics at the quantum level, you can at least that's why we're trying to look what's called the beyond the standard model. So this beautiful theory describing basically almost everything we know so far, and we've observed with extremely high precision with experiments. So the problem is that there are particles, or there are question marks and predictions made for certain particles which cannot be confirmed or even disproved by experiments, not yet anyway. Some of them being like gravitons, so gravity at the quantum level, dark matter, so different candidates for it, candidates theories for particles rather than string theory. It's one of the best theories so far, arguably for many people. We have to also assume the existence of superparticles, so superpartners, so supersymmetric particles that hasn't been confirmed yet. And there is no hint as of now, at the moment, that such particles exist. So that supersymmetry is a valid theory, or the string theory. It's a valid description of physical description of nature. So there's a lot of open questions, of course. That's where we're trying to address them. I'm aware of the fact, which is my understanding, that some people still think that the research which it's done so far, they don't understand the importance of the precision of experiments. When we measure something with so high precision, which we've been doing so far, which confirm theories that we've got, it does not, that's a proof that we're right, that we know what we do, and we understand what we observed, what it is. We understand the nature of what we theorized. We know, although there is a validity range. So everything we observed, especially things that we confirmed with highest precision, like extremely high precision with experiments, it's going to be correct, no matter what. And you don't need quantum mechanics to shoot a rocket to the moon, right? Newtonian mechanics is enough. If you want to use a GPS system, then you will need relativity. So you have to extend beyond this validity range. But the fact that if you want, for instance, to understand the elementary particles, you have to dive into quantum mechanics at that level, at that scale. It does not mean that the Newtonian mechanics is wrong. It's just a validity range, which is enough for some of the things, but beyond which there are other explanations which need to be defined with other frameworks extending a validity range. So everything we know pretty much everything there is to know in terms of a everyday life. Maybe we can, if we extend our knowledge and the validity range of the theories that we've got, the observations, we manage to extend observations via better experiments, better precision, confirmation or disproving some of the theories. It does not mean that it's going to cancel everything we know or revolutionize completely, like say, no, you were wrong about everything. So we should be confident about what we know. Assuming the existence of a level 3 parallel universe.
Okay, go ahead.
I am a big fan of the multiverse theory, and there are different concepts when it comes to multiverse, and Max Tegmark did a great job at classifying them, and he did this what's called the model of the hierarchy of the multiverse, and there are 4 different levels, and the first one is it's an extension of our universe. The second one is universes with different fundamental constants, so different physical constants, which is actually mathematics is the language with which God wrote the universe. So if you consider like the most fundamental elements or the building blocks of the universe, it's really like bits of information, and the most fundamental information is basically a physical constant, mathematical actually. So it's just fundamental constants. So you've got like the Planck constant, you've got the speed of light, for instance, and they led to our universe, so the way we it's structured. And that's the level 2 multiverse type. And then you've got the level 3, which is the many world, so Everett quantum mechanics, so the many world interpretation of quantum mechanics. Not everyone, like the branching of realities of parallel universes. And that's exactly the one I was going to mention, because and then you've got another level, so it's a ultimate ensemble. So that just to mention them, but the 4 of them. But the one that I was going to refer to was it's the in fact the level 3 branching of reality, so the mathematical parallel universe, where you're facing some choices, and at some point there is one conscious you in one universe and another conscious you in another one, so the exact copy of yourself, and you're both conscious in both universes, but just you made a choice. It doesn't necessarily mean, it's not that you're going to be a butcher in one universe and you will be a physicist in the other one. It's just a branching of the reality in terms of like decision making. You've got a choice that you have to make, and there are 2 different, let's say, 2 different options, and you choose one, and the other one is just going to branch in another universe, so the parallel universe. So the very technical explanation, just to ask you, how do you see yourself in this parallel universe, the parallel reality, so the branching of the reality? What would you do?
Oh, okay. I mean, I have no idea. It's a very difficult question, really. I mean, because that would mean I would have to be a different person in a way, right? I wouldn't want to do what I...
Not necessarily. Doesn't mean that you have to be a different person. You probably had different alternative plan B. Let's call it A prime, if you will.
Yeah. Well, I mean, well, first of all, I'm not entirely sure that free choice is something that exists. So, but I'm not sure if I could have chosen otherwise. But if you want to entertain this idea, I guess I would just went into some industrial, to some industry, to a company manufacturing some sort of, I don't know, machines, devices, maybe working with information technologies. I'm not sure. I would just go into one of those positions and see what happened. I mean, that was my plan B if the doctorate would not work out. but it did. And then, I don't think I had the choice to say no to it, basically.
And Sofia, so you mentioned before that you've got music is your passion, and you're passionate about art as well. So you paint, and that's pretty interesting because I've got the same, by the way. So, but I do electronic music, so you probably heard of it at least. And I like drawing and painting. I hope you've probably seen some of it. Had I not chosen physics, I would have ended up. I mean, I've always been split in between physics and music, but electronic music is just that physics is infinite. Like, we know so little. You've got so much to discover that it's not repetitive. It's not like, I'm not saying that music, especially if you've got you're creative, is kind of, it tends to infinity as well, but it's a different infinity. I think it's a bigger science. Really, physics gives you really a bigger infinity. So that's what I like. That's what triggered my interest in physics. But what about you?
Your discussion about parallel universe remind me of something. So I brought my thesis here. So I don't know if you can see it, but I designed this cover.
Wow.
Yeah, and this is like is an artistic interpretation of like a cosmovision of the observable universe.
Okay, yeah.
From the perspective of the human. So like center is the Earth, and then the stars and the galaxies, then the
oh, right, yeah.
The collapse of structures and the CMB at the very end is light. And I like it because when I start designing it, I thought like also looks like it like the proton, right? So in the back cover, I actually did like atoms, like either neutral atoms or just electron isolated. My work was mostly with hydrogen, also because they look a little bit like island universes. It's like many models. Maybe there are many more universes like this floating around in bubbles or whatever. I mean, it's obviously an artistic license, right? So yeah, I mean, maybe in a parallel universe, I was a musician. Maybe in another parallel universe, I am a neuroscientist, actually, because I am very curious. I'm pretty sure there's like a lot of, if the parallel universe exists, there's versions in which I am everything because I like so much stuff. I'm particularly prone to neuroscience. I think like it's the most interesting field in the sense of how much we don't know and how much can we learn, right? It's actually probably much more complex than what
it's amazing.
The formation of the universe is, like the mind is much more complex than all the connections of the galaxies that we can simulate.
That's another thing that I find fascinating, and I started to I do my kind of a side research, or if like topics related to neurophysics, neuroscience, but psychology as well, but they're somehow correlate. I mean, neurophysics is more like fundamental, right? I mean, the fundamental aspects. So it's psychology is like more applied, if you want. But it's amazing how the human is far from being understood. And it's even more, it seems like it's more complex than the universe. I mean, there's a different type of complexity, of course, but
and moreover, it's like a metacognition of the universe itself. It's the universe understanding itself. It's fantastic.
Exactly, and the fact that we don't even know, we don't really understand what consciousness is. We don't know. We've got no idea. We can't really define consciousness on a.
I mean, people are trying. There are some definitions, but
of course, yeah. But there is also Max Tegmark, the cosmologist. I was mentioning the multiverse hierarchy, his model, and he proposed consciousness as being one of the states of matter. It's very interesting. I went through.
I never heard about it.
Yeah. Isn't this the panpsychism concept?
The one I mentioned about Max Tegmark.
Yeah, it just sounds like panpsychism, that basically consciousness. Yeah, it's a consciousness as a property of matter, basically.
That's interesting. I'm not sure about how that relates. If that would be interesting to check out. But what I've seen is like more he uses formalism, like very mathematical, like with Hamiltonians and density matrices. Yeah.
There are even other crazy theories saying that like the universe outside of the mind doesn't exist. It's like the mind creating it. Just conscious beings interacting create reality rather than the reality exists by itself.
The metaverse, what is it called? Matrix, the holographic principle, actually, that you're basically just a projection. There are different, I mean, I've got my own theory about what's happening, which it's not clear how it manifests on our level, but I came up with an idea that probably I'm not the only one who came up with that, but that our consciousness, it's a packet, it's like a wave packet of information, like bits of information, so which is basically the most fundamental quantity. It's even more fundamental than elementary particles. It's basically information, so you can reduce it to like really mathematical values. But I believe that this information of quantum bits, if you want, so let's call them packets of quantum bits, which make up what we do not understand what that is entirely. So we call it consciousness. Once it's like, this is exactly what, I'm basically repeating what Roger Penrose said about it. He suggested that it's like a quantum software and we are like a hardware. So once the hardware stops working, there is no reason why the software should stop as well.
So you're saying you're a dualist, basically. You believe that consciousness is a different thing than matter, right? It's like, because there are two ways of thinking about this, right? Monism, that everything is basically the same thing, body, mind, or dualism, that the body and the mind are like qualitatively different things, right?
I basically am, yes. I do believe. I mean, I'm not entirely sure. I mean, I'm open. Of course, it's not like I don't religiously believe in one theory. I mean, I'm open.
Oh, it doesn't have to be religion at all, right? It could be physics, essentially, right? Because if the
I use the term just to say that I'm not strictly sticking to one theory more than, I mean, I think that makes sense. That makes sense to me with respect to my knowledge, because it's hard to question things that experts have suggested when you're not an expert in it. So I kind of follow I kind of follow this way of thinking because it makes sense to me and I like it, but it doesn't mean that I think that it's necessarily the most correct one. But I like to think of it as something which is really it's like a metaverse. It's a concept that makes, I mean, I think that the patterns that you see in nature at all scales, they tend to repeat themselves. I mean, that you can notice. It's like almost like a cliche point of view, but you can kind of think, what you see in the sky on the astronomical scale. You see nebulas and your eyes. So you can see your eyes and the pattern of the nebulas and what they look like. And you can find probably, well, we can argue that we've got the tendency to seek patterns and to kind of see similarities. But you can't deny that there are similarities and there are repeating patterns at all scales. So I think that by that logic, if the idea of a metaverse exists, and that we came up with it, and we came up with the idea that we can be, maybe we're just a projection of something that exists elsewhere. It would make sense to separate the two, like, you know, the matter and consciousness.
To think about this as this dualist approach is very tempting, I guess, because there's nothing that we have in the current physics that would explain how you can take a bunch of atoms, arrange them in space, and just a mind pops up like this, right? There's no explanation that we have, right?
That's exactly.
I mean, you can imagine how a machine that processes information is created, but the consciousness, the fact that there's somebody in there, you know, there's light inside, that's unexplainable at this point. And I'm not sure if we ever will going to get to the point that we can understand this, because consciousness is basically a subjective experience. Like, I don't have access to your mind and you don't have access to mine. And I don't think there's an obvious way to bridge this gap. So
I dare to argue with you about it. I mean, not argue really, but it's more like of a question, actually. So it's puzzling to me. You say you can't access my mind, my consciousness, but at the same time, you can understand my way of what you can understand what I think. You can understand to some extent. I mean, not everyone can what I feel. So you've got this cognitive ability to understand.
Oh, I mean, yeah, I'm not a neuroscientist, but as Sofia mentioned, this is a super interesting topic. So I read from time to time, and as far as I understand, this is because every person has a model of another human in their mind. So I can kind of model what you're feeling, but it's not 100% accurate, right? I can kind of guess what you're feeling and maybe guess what you're thinking, but I have no idea when you're looking at a green grass, how does it feel for you to observe the color green?
Well,
like this
actually,
is something I cannot access, right?
If I can comment something very briefly, there's a case of a pair of co-joined twins. They are attached by their heads. So they share part of their brain.
Okay.
And they can hear each other's thoughts. So they
see
what the other see.
You have to send me a link. This is amazing.
And they say, like, once Gary is like looking at something and the other one is describing what the other is seeing. So they get, I mean, they are still quite young, I think, but that's so fascinating. I mean, there's so many questions you can answer by just like sharing their minds. I mean, do they create like the way they see reality is the same or not? You know, like, did they create the same realities by like learning together how to grow, you know? Do they see the same green grass or not? Because like the other one sees the grass that she's seeing. I mean, you know what I mean?
Yeah, it's amazing, really.
It would be very interesting to, there's a study case for consciousness, actually. I'm not sure how much it's been done in that direction with that specific case, but that I think that would be very, it will be very interesting. And also, I think, well, by the way, it's fascinating and disturbing at the same time. So if I mean, I had to share all my thoughts with someone else, with even like, wow, a chaotic mind. I wouldn't want someone to see everything that's going on in my head.
I don't know.
I don't want to see it either.
I want to say one last thing, because it's like at the very end, it's also very physical. It's like the question of the observer, right? The observer influences the observation at the very root, right?
Not necessarily. No. Oh, you're talking about the measurement problem?
Yeah, I mean, in the sense that like an observer, once it makes an observation, it also modifies the thing that it's observing, right?
It depends on the point of view, because there are frameworks where you actually you say
when you actually have to actively. I mean, there are modifications that are so tiny that you don't care about, you know. But at the very least, when you observe, you influence the thing you're observing too.
there's different points of view. There are.
Yeah, I just wanted to make another observation, not exactly that point.
Okay.
I'm just saying in the sense like in the conversation of can we perfectly see each other's minds? And the answer is like, if you're going to do that, you're going to influence the other person's mind at the very end, right?
Oh, in that case,
so by observing, you change. Everybody changes, you know. I mean, these conjoined twins, you know, like will they could have been very different if they didn't share a mind, you know. But so like you're changing when you're observing, if you're sharing thoughts, you know.
It's not clear to me if you assume the
I mean, it has to be. I mean, I am the person I am because I receive perceptions of the world through all my life. If I was I had a different reality, you know, I would have been a different person because my perceptions also change. I'm not isolated, you know. I mean, I am the person I am because of my interactions with the world. So it will be the same case in a brain. If I have experiences from another brain, I will change myself too. You know what I mean?
But that's if you assume that there's free will.
There's no free will. That's a free will. Yeah. I mean, what is free will? It's like a human definition at the very end, you know.
Well, no, it's like the lack of it's not necessarily deterministic. I mean, it's lack of the determinism in the sense that.
I mean, there's no pure free will at the very end, right? Because every decision I will take will be based on whatever I experienced, you know, plus my own mind, which is also a combination of whatever was forming me, you know. So.
But in that case, if you assume randomness of events, so
yeah, that could be like a free will, but at the very end will be part of it, you know. It's part of the conditions that I'm set up to make the decision. You know.
But sorry, would randomness really be free will? That would be just chaos, right? It's still not you making the decision, just, you know, the whatever dice you have in your head rolling and ending up on, I don't know, you getting a glass of water or not. But it doesn't still sound like free will.
Unless
to
you
me.
decide to make the random.
Yeah, but like.
But again, it's a circular argument, right?
Yeah.
That's interesting, actually. The definition of free will is kind of it's misleading, actually, because it's kind of abused and used and misused, I think. But so we have to also agree upon the definition of free will. But I dare to argue that if you've got chaos, it's not really, is it deterministic? I mean, have you got determinism? I mean, you can end up with completely different outcomes depending on a very tiny change at the beginning. So how can you, I mean, to first degree, first order approximation, you can very well assume that if you assume a chaotic system, or what's going on in terms of your decision making, then you can say that there's free will.
Can you? I mean, if it's chaotic, it's still not something you can control, right? It just means that if you would replay the choice multiple times, you would have different outcomes, but not necessarily. It doesn't imply you can control it. Depends how the.
But that's probability then. That's not deterministic. That's randomness.
Sure, so but it's not a choice. Like, if you say I'm gonna choose a number and take a bunch of dice and roll it, and it's 7, you didn't choose 7. The dice chose it for you, right?
Yes.
And I'm just saying that your neurons are like dice. If you have this
idea. So yes, but then you're basically, so you're stating that in that case there's no free will.
Yes. I mean, I don't see a way of interpreting world that there's space for free will. Either deterministic or chaotic, neither scenario gives a space for free will. So by the way, it's not my idea. I'm quoting something that I read before, probably a remix of everything I read. So, you know.
At the very end, you can say like you have a will or a freer will. I don't know. I mean, if somebody forces you to choose between A and B, or somebody like makes you choose between A, B, C, D, E, F, G, you could say you have more will
Well,
in a certain way. I mean, it depends on at the very end is a definition, right? So you can define
exactly. So we have
like
to agree
free
on
will,
that.
where you have more options, right? Or ultimately you can make an option,
But the thing that I find very interesting in Philip's what Philip pointed out about you roll a dice and you get a number, but you choose another one at the beginning. So there is an element of randomness in this case, but there is also free will, because you say it's chaotic, so you can't really control it, which makes sense. And at the end of the day, whatever choice you make, the outcome, it will be outside of your field of choices. So you made it, it looks like you made a choice, but you actually, you can't really predict the outcome of that choice. That means that no matter what I choose and what I do,
I'm saying you're not choosing, is that the act of choice is essentially rolling the dice, if you assume not deterministic universe, right?
There is a probability, of course, that this choice is going to match the outcome is going to match my choice. So if I choose
I'm saying that there is there isn't a thing like your choice, right? Either it's predetermined, right? Because the universe is deterministic and every time you replay it, the choice is the same, or what you say, or it's chaotic. So every time you replay it, it's going to be different, right? But then the act of choice, the analogy that I'm taking here, this is rolling the dice. You're not making the choice. The dice are making the choice for you. So the chaos in the...
There are different levels of ignorance about, like, you don't really know. There are like too many parameters which are unknown to you. So you do not know what you're doing, what's happening. But let's say that you could, in theory, you could measure or calculate and predict the exact outcome, depending on the way you throw a dice. So there is a way to know, depending on how you throw it, what number you're going to get.
Yeah, okay, I see your point, but this is still, you're saying that there's a person rolling the dice, and I'm saying, no, that's not the case. The dice are...
I can control all the parameters, so I know exactly what angle, I know exactly what's the friction the dice is going to have.
The simplest answer is not the real answer. It's the most likely.
Yeah.
Just the most likely.
Most likely, of course. Yeah, extraordinary claims require extraordinary proof, so evidence. So it boils down to the Occam's razor. The most likely explanation between two candidates, it's basically the simplest one.
But sometimes the simplest answer is not the real answer. It's the most likely.
Yeah.
Just the most likely.
So it's like a probably first order approximation of what we think we know. It's beautiful to be able to share knowledge. I think that scientists should like stick together and build a very strong network and help themselves, so each other, as well as people, to understand the world, nature, the possibilities, how to cope. We're not many. So thank you very much for your time.
Good luck.
Thank you for participating and
enjoy science.
Have a nice evening.
Don't give up.
Understand
You
science.
too.
Makes good.
Good luck.
If you understand it.
Okay. Bye.
You have to switch, to something more digital that you're not really comfortable with, or you're not acquainted with.
You get pissed off because you're not comfortable with it?
Myself, no, I don't have that problem. I just have a problem with people who do have a problem with it.
A problem with the people who have problems.
Well, I've got many problems as well, so I don't have
Okay.
problem with people who've got problems, but there are people who get easily offended when you say something that they don't like. The thing is about having problems with digitalization, you know. So if you go digital, and there are people who actually avoid it, they could keep doing it, but they decided not to, because why bother? Why would I need to switch and to keep learning something that I'm not comfortable with, and I don't even need it? Now we're probably going back to the Stone Age. That's how I feel about it. You know, there are people who may not take it the right way, even though they may not be necessarily against. I mean, I'm not saying that everyone has to work remotely. And I mean, it really depends on the nature of what you're doing. The issue is that there are people who are trying to go, you know, back to the situation prior to COVID. I mean, you can negotiate always. You have to go to meetings because everyone is there, because it's better for you. The problem is when you prefer something and I have to stick to your preference. It's frustrating for me, or the other way around. So my preference is to stay home, but let's say that your preference is to be present in person. So if you work in person, I always stay at home. At some point, we may diverge. That creates a problem. It's about negotiation, so both parties have to agree upon, you know, mutual preferences. So you get my drift?
Yeah, it should be flexible within some boundaries, and some people are just used to some way of doing stuff and they want to go back to it. And
find a compromise that works for everybody. I mean.
Yeah, but the problem with that define what a compromise that works for everybody is. I mean, if I
find everybody should have a word to say. You know, they should accept diversity. You shouldn't like force everybody to come back, and they shouldn't force everybody to stay at home. I mean, except in pandemic conditions. You know, like.
Yeah, I mean, let's assume that I want to stay at home because I just feel comfortable with that, and I've got too many parameters which almost force me to stay at home if I want to be productive. So every time I have to be in person, assuming that basically it's purely theoretical, what you do is purely digital or virtual, you know, what I'm doing does allow me to stay to work remotely, not necessarily at home, but from anywhere. And it's not even a matter of preference, it's just a matter of being pragmatic so that you can produce and be efficient. So let's assume that and I have to be present because the environment forces me to, and it may be needed, but it's not like fundamentally necessary. So I'm going to be less productive every time I switch to a different work style. Someone can take a computer, someone can record the meeting, or they can, you know, adapt to it, and it doesn't require too much of an effort. I think that you have to weigh the impact of the effort that one has to make. When you make that statement, it's not clear that if I choose to stay at home, that should be something that I should be able to choose. Many think that if I make that choice, that I am not the one adapting, I'm not the one being flexible. And now here is a conundrum. Here is my question. How are you going to solve it? Well, you don't solve it, you just stick to the flow, and that's it.
I guess. Oh, okay. Well, then should I continue, or should we wait until it's...
Okay, I don't like the image I'm seeing.
Yeah, I don't know what I will do because the battery died. I will not have the same camera as before. It will completely change, so it will be a break.
I prefer. Well, I've got my rubbish laptop camera, so that works.
Me too.
Green screen. That's still great.
Hello again.
It looks like a little bit like photoshopped. Okay, so Sofia, you changed. You changed.
Well,
but you always look pretty. So.
Go ahead.
Okay. So hello everyone. We're here to talk about physics, and I've got my two hosts. My two guests. I'm a host. Yeah.
Sure. You got it.
I mean, I can't even focus because they're fucking doing something in my somewhere in that corridor, they're doing something, so I keep hearing. Can you hear it?
Should have like a section of bloopers at the end.
Yeah.
With some beep, beep, beep.
For fuck's sake, I mean, I'm trying to focus and they're doing something. They start at 7 a.m. Well, you woke up at 5 a.m. because you couldn't sleep anymore. That's a different story. I am like, many physicists, they work. Actually, I found out because I didn't know about that Alan Guth, for instance, and Newton, who I'm a big fan of, he used to work basically at night, but Newton, he claims that he was rested, that he woke up after 4 hours, but that was sarcasm probably, because you can't be rested. By the way, there is an article saying that there are a few people who can sleep 4 hours, 4 to 5 hours, and they're like
My mother sleeps like 4 or 5 hours and she's fine.
But they don't need to sleep more, because it's about the cycle. To have at least 4 of them, and each of them, it's like almost like 1.5 to 2 hours, and you need to have 4 of them. So every time, and by the way, if you wake up in the middle of REM phase, you're completely like you're dead. So that's why it is better to wake up after 20 minutes if you're taking a nap, because you've got the phases and you're not in the REM phase. So it's like the worst thing that can happen to you if you're napping is when you wake up, you break that, because you're more paralyzed, you're more like switched off. Anyway, so you wake up before, it's like right before it, because you've got like a flat sleep or very superficial, and then that's why sometimes I slept 3 hours, but I wasn't dead when I woke up. I'm just dead now, so that's why I can't focus. But
so it's not. Sometimes I'm feeling I'm sorry, this class is just so annoying. Just give me a second.
No, it was nice talking to you. Okay, bye. I go.
Don't get discouraged.
Hold on a second. Okay, so thanks.
Enjoy science.
With that, no. Yeah,
Science can be a beautiful thing, but also a terrible thing.
Yeah, I like my small universe or galaxy, whatever. You can interpret things the way you like it. So as long as you're talking about the same thing, we have to agree on the subject. We have to agree on a definition.